Good afternoon, everyone. Thank you for joining us. My name is Marissa Waterman. I'm the Marketing Director here at the Academy. Today's webinar is titled Delivering New Water Plant Upgrades to Improve Performance. Our Executive Director, Dr. Daniel Uther, will serve as the moderator and will introduce our speakers today. During the presentation, you'll be able to submit a question by clicking on the Q&A icon on the bottom of your screen. We'll do our best to address each question at the end of the presentation. Before we get started, Dan would like to say a few words. Dan, how are you today?
I am fantastic, Marissa. Thank you. Hello, friends and colleagues in the audience. Great to have you with us. You know, it's that time of year when the Academy begins to send out reminders for annual renewals. And if you're anything like me, every time you get one of these, you pause and you ask yourself, what am I getting for my membership fees? That's a great question to ask. And today's webinar is a fantastic answer to that question. The Academy offers diverse programs to our members, including this fantastic webinar series. We've got about 24 events spread throughout the year, which means you have access to more than 30 hours of continuing professional development, all for the price of membership. And that's a huge value for money. It clearly makes the Academy worth it in my book. Of course, there's a lot more to the Academy, and we're glad to offer folks a variety of programs. For example, we host the annual Excellence in Environmental Engineering and Science competition. And today's webinar is an example of a project that was recognized with an award in 2024. Specifically, the Ashtabula story delivering new water plant upgrades to improve performance was recognized with our honor award in the design category in this year's competition. In addition to membership dues, the Academy programs are also financially supported by the generous contributions of our patrons. Those are the organizations listed on this slide. They are firms and utilities that provide additional financial support because they care deeply about the profession. So as we begin our webinar today, please join me in saying thank you to our patrons. Thanks for supporting our 5-year strategic goal to grow, connect, and diversify the environmental profession by sharing the stories of our members. And today is one of those stories. Today we'll hear from Adam Arnold and Rich Atulican, both with HDR. Adam is the water treatment business class leader, and Rich is the senior vice president and a board certified environmental engineer. I'm honored to introduce this award-winning project. Adam and Rich, your project delivering new water plant upgrades to improve performance is something we are all excited to hear about. Colleagues, as a reminder, please put your questions in the QA function. I'll do my best to include all of these in a moderated discussion at the end of today's presentation. And now, Adam and Rich, the stage is yours, my friends. We are so excited to hear from you. Thanks for joining us.
Thanks, Dan, and good afternoon, everyone. Thank you so much for joining us today. Rich and I are very excited for the opportunity to talk about an Ohio-based collaborative delivery project that we were involved in, which included a combination of new and rehabilitated historical water treatment infrastructure. It was a unique project for several reasons, not the least of which was because it had to be completed from start to finish on a tight timeline during the height of the COVID-19 pandemic. To offer a little more about myself, I graduated with bachelor's and master's degrees in environmental engineering from the University of Waterloo in Ontario, Canada, where I grew up. Following graduation, I spent 3 years working for a small Ontario-based consulting firm, designing municipal water treatment and conveyance infrastructure. I was then hired by a small startup company in Northeast Ohio to develop and test closed-loop water recycling systems for residential and commercial facilities, where I learned a lot about complex water treatment processes. And I started with HDR almost 6 years ago in the Cleveland office as a project manager, leading some exciting projects like the one that is the subject of this presentation. With all of that, I have over 16 years of industry experience. Rich, do you also want to expand a bit on your background?
Sure, Adam, I'd be happy to. Good afternoon to some of you in the East and good morning to everybody else. Rich Atulican. I have 47 years of industry experience. I spent the first 34 years with another large environmental engineering firm and joined HDR and actually started HDR's Cleveland office in 2011. My background is both water treatment as well as wastewater treatment, and I've been involved in just a number of different delivery mechanisms, from design bid build to CMAR to the progressive design build that we're going to talk about today. So let's get started, Adam.
Yeah, thank you, Rich. Yeah, you certainly had an impressive career, and I certainly feel fortunate to have the opportunity to work alongside you, and I'm appreciative for your continued mentorship. I'll be the presenter for the first half of the presentation, covering the project background and key aspects of the initial planning or pre-design efforts. Rich will then present on the design approach, walk you through the construction activities and performance of the facilities post-construction, and provide a summary of lessons learned. Typically, we're giving this presentation to a room full of drinking water professionals, and it's my understanding that today's attendees might have a broader range of knowledge on the topic. So I'd like to take the first couple of minutes to run through some fundamental concepts and lingo so that anyone new to drinking water treatment is hopefully not too lost as we progress through the slides and the information. Starting with the approach that's taken when we as designers are tasked with designing a new or upgrades to an existing water treatment plant. The first step is determining the level of treatment that's required or desired based on the source or raw water quality, as well as the regulatory requirements, utility goals, and or even customer preferences relating to finished water quality. From there, we work with the utility to select treatment processes and technologies, figure out how to move the water through those processes based mostly on site elevations, select and size all the equipment needed, including pumps, valves, and instruments, and then work with a broader team to design the supporting infrastructure, including the tanks, the buildings, piping, electrical equipment, HVAC, and plumbing. And concurrently with that effort, we work with the state oversight agency. In Ohio, it's the Ohio Environmental Protection Agency, or EPA, for example, to obtain a permit to construct and operate the new or upgraded facilities. There are quite a few processes and technologies that are commonly employed for water treatment throughout the US, some of which are not that costly to build and operate, but require large tankage, and others that are more compact, but the operation requires a lot of electricity and man hours, for example. So the selection of these processes and technologies commonly depends on the factors listed here. Raw water quality and finished water quality, as I mentioned, but also operational complexity as compared to the familiarity and capabilities of the utility staff, available land to build the facilities, and funding to cover both the capital expenditure and ongoing operations and maintenance costs. There are three traditional raw water sources for drinking water: groundwater from an aquifer, salt water from the ocean, and surface water from a lake or river, though water reuse is becoming more common in areas where water availability is a concern. They all require, or generally require, different treatment processes and technologies. Our focus today is on surface water treatment, and so this flow diagram represents a typical plant for that application, starting with pumping of the raw water to the treatment infrastructure. Flocculation and sedimentation are considered pre-treatment processes designed to remove a vast majority of the particulate material, including organics, through settling. A chemical called a coagulant is added ahead of the flocculation tanks, rapidly mixed in to facilitate the formation of larger, more settleable particles known as floc. Settled water that discharges from the sedimentation basins then passes through filters, most commonly gravity filters that contain several feet of sand and or anthracite for absorption of organics. Though there are several disinfection options, chlorine is typically added to the filtered water, which is stored in clear wells prior to being pumped out to the customers. Anything that's removed from the raw water in either the tanks or the filters makes up the sludge, and those residuals can be handled on site or discharged to a wastewater treatment facility, depending on its makeup and local codes or ordinances. And there are other chemicals commonly applied for various purposes, but we don't really touch on those in this presentation. And finally, we have some key water treatment terminology listed out on this slide. Turbidity is a measure of the clarity of the water, measured in net fluvimetric turbidity units, or NTU. It's relatively easy to measure and is therefore commonly used as an indicator of treatment performance. Raw water turbidities can range anywhere from a few NTU in calm lakes to over 1,000 NTU in fast-moving rivers after a storm event, for example. Total organic carbon, or TOC, is a measure of the amount of carbon in organic compounds in water and is also commonly used as a treatment performance indicator. Contact time, or CT, is the amount of time needed for chlorine to disinfect the finished water before it reaches the first customer, and is a function of the free chlorine residual, which is the amount of chlorine available to kill pathogens. Disinfection byproducts, or DBPs, are chemicals that form when chlorine or other disinfectants react with organic matter in water and may pose health risks. Several types of DBPs are currently regulated, including total trihalomethanes, TTHMs, and haloacetic acids, HAA5. And harmful algal blooms, or HABs, are excessive toxin-producing algal growth. So with that basic understanding, the Ashtabula Water Treatment Plant is located along the southern shore of Lake Erie, near the Pennsylvania border, about 60 miles east of Cleveland. The facility employs conventional processes for treatment of raw water that's generally good. There are periodic turbidity spikes, primarily due to adverse weather conditions, and HABs have on occasion extended out to Ashtabula from the western basin of the lake. They also on occasion have to deal with clogging of the intake from freezing in the winter. And just for reference, that serpentine body of water is an on-site lagoon to capture any water treatment residual products, such as settled sludge from the sedimentation basins, and the treatment infrastructure is just south of that. The Ashtabula Water Treatment Plant is owned and operated by Aqua Ohio, the largest investor-owned water and wastewater utility in the state, and has an approved rated capacity of 10 million gallons per day. It was originally constructed in 1887, then rebuilt in 1908. The facility has subsequently been expanded several times, including in reverse chronology, a new chemical building constructed in 2014, additional flocculation tanks constructed in the late 1990s, and Aldrich units constructed in the early 1950s. And Aldrich units are the domed circular tanks right in the middle of the property and consist of a center settling tank and filter along the periphery. It's kind of an all-in-one technology with a compact footprint that was popular in that era. New clear wells were also constructed in the early 1950s with relay pumps to deliver water from the original clear well under those filters, or under the filters, to those above ground tanks. These photos are from the 1908 rebuild, including construction of filters and flocculation sedimentation basins. The building with the conical roof is the original well house. And a fun fact that we learned last week, before any pumps or treatment infrastructure were installed, water was transported to the citizens and businesses of Ashtabula from the well house via horse-drawn barrels. So we're dealing with very, very old infrastructure here. And that structure is still in place, now serving as the raw water pump station. One outcome of the numerous subsequent expansions is that they ended up with two distinctly different treatment trains, splitting at raw water pumping and combining at the elevated clear wells. And the operators said that operationally, it was like having two separate plants on one site. And that was problematic from a hydraulic standpoint. It was difficult to balance the flows through each treatment train. It was also becoming difficult to meet water quality goals because of the flow split and for a variety of other reasons, including aged and deteriorating infrastructure, shearing of the flock, sludge accumulation, and lack of flexibility and automation. Furthermore, in addition to the intake, some of the basins and key process equipment were prone to freezing. As a result, Aqua developed a multi-year 5-phase approach to reconstructing the Ashtabula Water Treatment Plant with the intention to replace infrastructure that's reached or had reached or exceeded its useful life, improve flexibility, implement state-of-the-art automation, and ultimately address operational and performance issues. Phases 1 and 2 were to be focused on upgrading the original filter and clear well building and bettering the clarification processes respectively. And phases 3 through 5 would replace any of the existing infrastructure that remained after the first 2 phases were completed. In February 2020, a request for proposal was distributed to progressive design build teams, which covered design and construction of phases 1 and 2 and development of a plan to fully replace the facility over a 15 to 20 year planning horizon. The RFP required any improvements to be in use and useful by the end of 2021, and this was essential to meet requirements of the Public Utilities Commission, meaning that recovery of the capital cost was only possible if the infrastructure was treating water on that schedule. Aqua selected the Great Lakes Construction HDR team for the project and issued notice to proceed in May, which allowed for only 19 months to final completion. And of course, COVID-19 restrictions were well in effect. Given the tight timeline, we moved quickly upon receiving that notice to proceed, following what we called a fast start approach in our proposal. Field activities, including geotechnical and hazardous materials investigations, as well as structural condition assessment of the existing facilities, were scheduled to occur concurrently with workshops with Aqua's management, engineering, and operations staff. The primary objectives of the workshops are listed here and include classifying the performance and operational issues, identifying and assessing feasibility of process alternatives and technologies, and developing concepts. The pandemic presented challenges to holding the workshops, but we worked through it because collaboration was understood by all stakeholders to be critical to building consensus, leveraging past experience, and most importantly, facilitating timely design development and Ohio EPA approval. The workshopping began with establishing water quality goals for the plant, which generally aligned with regulatory compliance requirements, but in some cases were more stringent based on Partnership for Safe Water performance goals and/or internal standards, such as with the DBPs, TTHMs, and HA5. And for reference, the Partnership for Safe Water is a voluntary cooperative effort, including several large drinking water organizations, including the US EPA and American Water Works Association, and over 200 utilities, including Aqua systems, with a mission to improve the quality of water delivered to customers by optimizing water system operations. We then reviewed historical source water quality and performance data to verify and/or identify issues and to establish a baseline. During the 5 preceding years, 2015 through 2019, source water temperature swung from near freezing in the winter to over 25 degrees Celsius in the summer, nothing untypical for Lake Erie. Over the same time period, seasonal fluctuations in source water turbidity were also expected and observed, though it wasn't too excessive and was predictable over time. For reference, the green and blue lines on all the plots represent the 5th and 95th percentile respectively. And so the wider the gap, the more variability there is. The average source water turbidity was just below 19 NTU. Many of the higher 150 NTU plus values, which mostly occurred in the spring and fall seasons, anecdotally coincided with periods of heavy rainfall and or high wind events. Treated water flow has not significantly increased over time. Average day treated water flow was 5.1 million gallons per day, with a maximum day of 7.3 million gallons per day. Higher flows were observed during summer months, but there was a tight range indicating very little variability. Conversely, settled water turbidity worsened over time, with seasonal fluctuations corresponding to fluctuations in source water quality. Peaks weren't dampened, as evidenced in this plot. So the data supported the need to improve clarification processes with an average settled water turbidity of 2.7 NTU and a maximum of over 15 NTU. And those values are above typical industry guidance and Aqua's goal of achieving less than 2 NTU for optimal performance of the downstream filtration process. This plot is a little bit cluttered, but it pulls together source water temperature and settled water turbidity with coagulant dosage, which at the Ashtabula Water Treatment Plant is alum, injected, as I mentioned, pre-clarification to improve settling performance. As shown, alum dosage increased from about 20 milligrams per liter to greater than 35 milligrams per liter during winter months when water temperature decreased, but there was not corresponding turbidity reduction performance improvement. But despite variable and sometimes poor influent water quality, filter performance in terms of turbidity reduction was stable, as evidenced by consistently low finished water turbidity. The average was 0.05 NTU with a 95th percentile of 0.08 NTU and a maximum of about 0.2 NTU. That 0.7 NTU data point was previously determined to be an analytical error. So Aqua was consistently delivering high quality water to their customers, but filter run times were half to even a quarter of what was desired and typical at other similar conventional surface water treatment facilities. So those filters had to be removed from service and cleaned more frequently with large volumes of finished water, resulting in a loss of efficiency, and was also time consuming for the operators. We looked at sodium hypochlorite dosage, which varied seasonally as well, corresponding to temperature fluctuations. Average sodium hypochlorite dosage was 3.5 milligrams per liter, and there was quite a bit of variability. It got as high as 6 milligrams per liter. Aqua doses sodium hypochlorite with consideration for maintaining a free chlorine residual concentration of 1 milligram per liter at all points in the distribution system. And in general, the concern here is DBP formation potential, particularly in the summer months. The other key factor for DBP formation is natural organic matter. For the treatment techniques applied and the source water TOC and alkalinity concentrations that are typical for Ashtabula, a minimum TOC reduction of 25% should be attained. And as shown on this plot, average TOC reduction 2015 through 2019 was only about 20%, indicative of underperforming chemical coagulation and clarification processes. So this information only amplified concerns about the infrastructure that was in operation at that time. Aqua did have an extensive data set of DBP concentrations from sampling within the distribution system, collected from 4 different locations. In general, both TTHMs and HA5 have been elevated, periodically reaching the maximum contaminant level, or MCL, dating back to 2015. Of particular note, concentrations did not fluctuate seasonally, and there was a noticeable increase in 2017, possibly relating to a sodium hypochlorite feed adjustment and other factors, including the frequency and duration of distribution system flushing. Finally, HABs have become increasingly common in Lake Erie throughout the summer months, but as I mentioned, are known to primarily affect water systems in the western basin in and around Toledo, for example. As evidenced in the table shown here, concentrations of microcystin, toxic substances released by the algae, have been occasionally measured in the source water, and genetic markers are common. But in the finished water, microsystems were only ever non-detect. So in summary, retaining the rated and approved 10 MGD capacity was determined to be suitable and desirable based on historical and projected treated water flows. Primary ongoing performance issues were identified as elevated and variable settled water turbidity, low TOC reduction, and corresponding DBP formation with concentrations that periodically reach the MCL within the distribution system. Clarification process improvements were already planned for reconstruction phase 2, which were intended to address the settled water turbidity issue, but also anticipated to improve, maybe not fully rectify, TOC reduction and DBP formation issues as well. In addition to establishing water quality and treatment performance goals, the workshops also facilitated the establishment of operations goals. Most of the primary processes were still operated manually at this facility. In addition to lack of automation, a primary issue of concern operationally related to the split and distinctly different treatment trains. Aqua was also concerned about critical single points of failure. So the first 2 phases of reconstruction were designed, or to be designed, assuming 24/7 manned operation. Aqua wanted key decisions to continue to be made by operations personnel. Integration of automation was to be focused on simplifying operation of individual process units only. Design philosophy regarding redundancy included minimizing critical single points of failure and ensuring that approved capacity could be achieved. And the operations personnel requested that all equipment be accessible for operations and maintenance without the need for confined space entry permits. With consideration for the performance issues identified, as well as Aqua's goals, the design build team presented a listing of available process technology alternatives, including a broad assessment of contaminants typically encountered in Ashtabula and expected performance to identify the most applicable technologies. And through this cursory exercise, including discussions during the workshops, the list was narrowed to 3 technologies for concept development, 2 of which had already been employed at the plant: coagulation, including flocculation and settling, and conventional filters, but also low pressure membrane filtration, microfiltration, and ultrafiltration specifically. HDR's developed a planning tool called Water Spaces that allows our engineers to expediently produce high-level planning information. Outputs from this tool include spatial, cost, and operating information that allow owners such as Aqua to compare competing concepts and provide an understanding of relative benefits and costs. We employed Water Spaces on this project as part of the workshopping to efficiently assess concepts for the first 2 reconstruction phases. Relating to the first phase of reconstruction, 2 concepts were developed for further evaluation. The first being improvements to the 1908 conventional filters, as originally identified in Aqua's RFP. And the second was a brand new ultrafiltration membrane facility with integral cleaning infrastructure. Though the capital and operating costs are typically quite high relative to other options, Aqua wanted to at least consider ultrafilters because they offer consistently high treatment performance. Additionally, the systems are highly automated, including the cleaning operations, and meet performance expectations quickly following startup. They also have the potential to address long-term changes in lake area water quality and/or more stringent regulatory requirements. The 5th phase of reconstruction involves the construction of new filtration facilities. So in essence, this would allow 2 phases of the project, near and long-term filtration, to be completed at once. For the first concept, the existing piping would be removed and the existing filter influent flume would be dewatered and converted to a dry pipe gallery. This would be necessary to accommodate all the new equipment, including control valves, piping, instrumentation, and control cabinets. Structural improvements would also be necessary, specifically on the interior walls, to support the change in loading condition. For the second concept, a new ultrafiltration building would enable flexibility in location, orientation, and other included functions. It would generally be sized as shown here and would include racks of ultrafilter modules, feed and backwash pumps, cleaning solution storage and feed facilities, as well as electrical and control panels. The facility was envisioned to be entirely standalone and could be constructed without any significant impact to plant operations, minimizing risk of service interruptions to the customers during construction. Regarding the second phase of reconstruction, 3 concepts were developed for further evaluation. The first was a new flocculation sedimentation building with integral inclined plate settlers. The second was retrofitting the 1908 flocculation sedimentation basins, including inclined plate settlers as well. And the third was rehabilitating the existing Aldrich units, including process structural and mechanical enhancements. Plate settlers were factored into the first 2 concepts at Aqua's direction because they offer improved performance over conventional settling basins, thereby maximizing filter runtime. They're similar in concept to tube settlers in that they decrease vertical settling distance for the particles, though deeper plate racks allow for a more compact footprint and therefore more flexibility on siting, and they also tend to be more durable. Additionally, plate settlers can accommodate hydraulically driven sludge removal as opposed to pumping, with minimal or no impacts to treatment performance. For the first concept, the process would include 2 trains of 5 million gallon per day rapid mix units, 3-stage flocculators, and plate settling basins, which would result in an approximately 125 foot by 50 foot building. Like with the ultrafiltration building, this would be a standalone facility and therefore provide flexibility on location and less risky construction. The limiting factor on siting would be hydraulically incorporating the tankage into the existing infrastructure, maximizing the driving head of the filters, but preventing the need for an intermediate pumping step. For the second concept, the existing structures would have to be structurally modified to accommodate the same process and equipment as defined for the first concept. And in fact, the overall footprint of the basins would have to be expanded, or the 1998 flocculation basins would have to remain as part of the overall setup to make it work. But the idea here was to maximize the use of the existing infrastructure. Similarly, for the third concept, the Aldrich units would be substantially modified, including removal of the tank domes, demolition of the perimeter filter ring, raising of the sedimentation tank wall, and installation of new process equipment and dome structures. All of that would, of course, require careful planning for maintenance of plant operations. The final step of the workshopping relating to the first 2 phases of reconstruction involved developing budgetary construction cost estimates for the combined filter clarifier concepts to complete the picture, as well as determining a preferred concept. Aqua initially eliminated 3 of the 5 concepts from receiving further consideration. Firstly, there is no current manufacturer of Aldrich units. Modifications would be custom, which could carry high risk due to any number of unknowns. Even if full restoration were achieved, they were worried that satisfactory performance wouldn't be assured based on their prior operating experience. Secondly, the 1908 flocculation sedimentation basins couldn't directly accommodate new processes and equipment, and the age of the concrete and structural reinforcing and potential related risk was concerning. So they wanted to move forward with a new flocculation sedimentation building incorporating inclined plates. Life cycle cost analysis comparing improvements to the 1908 filters and a new ultrafiltration building tipped the scales in favor of the improvements. But Aqua will likely reconsider ultrafilters for reconstruction phase 5, particularly if capital and operating costs decrease and/or conditions change. As an aside, Aqua is considering converting the 1998 flocculation basins now to contactors for powdered activated carbon, which they already add to the raw water to facilitate improved organics removal and address HABs sometime in the near future. This will require some structural and mechanical modifications to the basins, but the additional contact time would help to further improve TOC reduction and DBP formation issues. The last workshop we held was focused on developing a conceptual site layout for the future phases of reconstruction, as required by the scope of services, but also for consideration in the new flocculation sedimentation building and filter improvements design effort. More specifically, we wanted to be sure that whatever we do now does not in any way hinder the plans for a subsequent upgrade, both in terms of siting and hydraulics. This image shows the proposed layout of the infrastructure after construction of the planned phase 1 and 2 improvements, highlighted in beige. The layout on this slide represents the future condition following all phases of reconstruction, including the new raw water pump station, new filters or membranes, high service pump station, clear well, and administrative building, highlighted in blue, and essentially shifts the water treatment plant to the eastern portion of the site. And that shift is a bit more obvious in this layout, which is the future condition, including removal of the facilities that would be earmarked for demolition. And with that, I will turn it over to Rich.
Okay, thanks, Adam. And again, hello. So we're going to talk about design and construction, commissioning, and training and closeout in this next half of the presentation. And as Adam said, a lot of care was taken in terms of evaluating what the future plant would look like and ensuring that the improvements in these first 2 phases were consistent with that plan, both from a site layout as well as from a hydraulic standpoint. So the design goals were to modernize and improve clarification, as Adam talked about, correcting hydraulic issues and having a single train, by doing a better job of settling up front of the filters. Longer filter run times would be expected, and to continue Aqua's fine track record of delivering safe, high quality, and reliable water to their customers. So on the filters, the objectives were to improve process control and performance, correct the existing hydraulic issues again, and to provide better maintenance access to the filters. We also wanted to include the chlorine disinfection contact time. Adam mentioned that you chlorinate the water to kill pathogens and other harmful organisms. And it's prescribed in terms of how long that contact time and what the chlorine dosage needs to be in order to achieve those goals. So we wanted to get better disinfection compliance, but we didn't want to build costly more storage as part of this phase. We also wanted to utilize the existing structures to the greatest extent possible, maintain operations during construction, obviously, because this is an operating facility. And those were the challenges and the objectives that we had laid out. Our design approach was to balance new and existing treatment processes. And Adam talked a little bit how we came to the selection of what we wanted to collectively implement in this project, looking at things like affordability and space limitations, understanding the existing hydraulic characteristics and constraints within the existing plant, review the known limitations of performance. And Adam touched on some of the analyses that we had done on looking at existing water quality. We also assessed the condition of the existing structures and determined what their asset potential would be for future use, continuing through this project. To do all of that, what I've learned over the years is it is imperative to spend time with the operations and maintenance staff, the folks that live at the plant every day and know the plant inside and out. And we wanted to make sure that we understood what they're dealing with, what their concerns are, what their constraints are. We wanted to work with them to develop access for safety and service interruptions through construction. Adam touched on providing more automation in this plant. So we work with them to understand what they wanted to operate automatically, what they wanted to operate manually. And then again, to develop that vision for what the new facilities would look like when all the improvements were made. The tool that we used for the design that we always use is 3D BIM. In this case, we used a Revit product from Autodesk. And really the benefits of using that product are you're designing everything in 3D, you're pulling in equipment sizing from the manufacturer or recreating it to actual dimensions. So it really enhances O&M reviews with Aqua staff. They could see how much space was around a flocculator. They could see how much space was around the valve. And comment as to whether they thought it was enough or whether they thought it needed to be a little bit larger to allow them to operate and maintain the facilities. In addition to that, the 3D BIM design allows the schedule to be compressed because you're designing the facility in 3D and then you're cutting sections and plans from that model as opposed to developing separate plans, separate sections, and then having to update all of those when a change is made. It also increased team collaboration and improved interdiscipline coordination. You could see in the model whether, for example, you had a pipe potentially running through an HVAC duct. 3D BIM design really is the nexus, in our opinion, I think the industry's opinion now, as to where design, construction, and operations and maintenance intersect. This is just a view that shows the building as we had developed it on the left in the model and what it actually looked like. This is the filter building. In the left, you can see the existing is grayed out, and then we added a new vestibule, excuse me, to the right of that. We also used it to model the inside of the flocculation sedimentation basins. As you can see here, the 2D drawing, the 3D model, and an actual photo of the constructed facility. Similarly here, this is in the filter gallery. To the left, you can see all the piping that's in the filter gallery. And by the way, the existing plant had evolved to the point where that entire channel where all that new piping had been flooded and used to feed the filters with submerged valves. We were able, through this project, to be able to clean that up, put in new piping in a dry gallery, trying to maximize the accessibility of the operations and maintenance staff to be able to get to those valves. And then in the middle, you can see, again, the 3D renderings from the model, and then to the right, an actual photo of that filter gallery. This is just another view of the filters, showing the filter cells. To the left is the model with the green piping and the yellow piping and the actuators for the valves and the gates, and then to the right, actually showing what the filter cells look like. This is what the flock sed basin looked like, again, in the model, and an actual photo of it. We did not model the trucks, in case anybody is curious, but we could have if we wanted to. In addition, in the flock sed basin here, you see a drawing in the upper left that shows basically we had originally designed this project using bar joists. And because this was in the middle of COVID, because Amazon was building a number of facilities, we had heard back, Great Lakes Construction, I should say, had heard back that the bar joists had an exceptionally long lead time. So this is one of the benefits of design build, is where our collective team, the Great Lakes HDR team, did a redesign of the roof support structure using steel beams, which could be procured a lot more readily. And we were able to maintain schedule by being able to pivot that quickly. Just another shot that shows the support structure for the flock sedimentation basins, the model, and then what it actually looks like. What's very important on any of these design build projects, and especially on drinking water treatment, is developing a good relationship with the regulatory agency. As Adam said, here in Ohio, it's the Ohio EPA. And because of the fast track nature of the project, we spent time meeting with them early, informing them of the project, talking to them about some of the thoughts that we were looking at in terms of technologies, particularly the lamella plates that Adam talked about, because prior to this project, there were no lamella plates in any of Ohio's drinking water facilities. So we met with them early. We walked them through the plans, and then we submitted the plans, and approval happened in 90 days. And again, this was during COVID, when typical review times were significantly longer than that. As I mentioned, this was the first inclined plate installation in Ohio. As Adam mentioned, inclined plates are a lot more efficient in terms of the constructed cost than tube settlers, and certainly conventional sedimentation. And what we did there was we set up some calls between Ohio EPA and some other utilities that we had worked with in adjacent states, such as Kentucky, that had plates and had data to prove their reliability. So this saved probably $1 million or more in project cost by being able to get this approved and working closely with Aqua, Great Lakes, and Ohio EPA. So now let's talk about construction. And we've mentioned that our construction partner on this project was Great Lakes Construction. We came together early before the request for proposals was out. Great Lakes and HDR both have a similar culture, a culture that's focused on client service, that's focused on delivering quality, and also focused on meeting schedules and budgets. So, as noted here, in terms of the construction sequence, Phase 1 and Phase 2 needed to progress concurrently. And again, Phase 1 was rehabbing the existing filter building, as we've talked about. Phase 2 was constructing a new 10 MGD flax-seed building, as Adam had shown. So we spent a significant amount of time brainstorming with Great Lakes in terms of developing a sequence of construction, working with Aqua operations staff to talk about where the particular items would need to be cut in, the new items, what sort of tie-ins would be required, and spent a lot of time really planning on how we were going to do that. And again, the timeline is I think Adam had talked about earlier, was the RFP came out in February of 2020. We were selected in May of 2020. Construction started roughly 6 months later, after the design was taken to about a 60% level of completion and issued for construction drawings developed and a guaranteed maximum price negotiated. And again, we had to get the project done with water flowing through it by December 31st of 2021. So there was basically 6 months to build the project and 12 months. 6 months to design the project and 12 months to build the project. And again, the consequences of not meeting this schedule would be that Aqua, as an investor-owned utility, under the Public Utilities Commission's watch, would not have been able to recover on their capital for this project. That would have been deferred until the next cycle, which might have been 2 years later. So there was a lot of time pressure on this. In terms of subcontractor and major supplier selection and performance, there was a lot of coordination, as it says here, between Great Lakes and HDR and Aqua, and that coordination and the reach out from Great Lakes to their key subs and process equipment suppliers really facilitated that, the way that went very well. They looked at experienced local contractors, Aqua already had a selected system integrator with knowledge of their facilities that was brought onto the team for the programming of the PLCs. There was a lot of early engagement with those subs during the preliminary design phase. And during construction, subcontractor coordination meetings were held regularly, including 3-week look-aheads, and those were communicated proactively to Aqua staff to make sure that the work that was being forecasted to be done would fit within their operation boundaries. So now we're going to just go through some photos of construction. What we're looking here is at some of the existing piping and the new piping for the filters in the vestibule, which is in the front of the filters that got added on here. And this was really done in order to be able to bring the water from the new sedimentation basins into the filters via piping and get it out of that center gallery that we had talked about previously, that was submerged with a lot of existing piping and valves. So this was the first step to get that cleaned up. This is just a drawing here that shows the filters, the rectangular boxes that you can see on the top and the bottom, and then the filter gallery where all the piping is. And that piping not only feeds the filters, it also takes the filtered water away. It also conveys backwash supply water in order to backwash the filters, and takes the backwash waste away to the lagoons, and also air scour piping is included in there. And to wash a filter, many utilities use water alone, and also a number of facilities use water and air in combination to provide a really solid filter wash. Here we're just looking at some photos in the upper left that shows the backwash troughs. You can see there in green. The photo kind of in the center at the bottom shows that filter gallery with some of the piping installed. And at that time, the top slab had been removed and to provide better access for the installation. And then it was ultimately replaced with grating to allow Aqua access to get in and remove any motor operators or valves that they may need to in the future. This is just another shot that shows the filter gallery under construction on the left, and then the filter gallery completed on the right. Adam mentioned there's an intermediate clear well that's located under the filters, and this is pretty common in water treatment plants. As the filtered water goes through the filters and it gets drained into a clear well below, where chlorine is added and disinfection contact time is achieved. And as Adam mentioned previously, as this plant was expanded in the past, additional clear well volume was provided by those 2 circular standpipe tanks that you saw from the site renderings and the site drawings that he had shown previously. This next drawing shows the flocculation sedimentation structure, again, which was a new structure. I don't think you can see my cursor, but to the left, far left, you see 2 circles. Those are rapid mixers. The chemicals that Adam mentioned are added there and mixed into the water stream. The water then goes into these flocculation stages. We have 2 trains, each with 3 stages, that basically take the alum, take it with the solids that are in the water, and it creates larger flocks, which can be then settled out in the lamella plate sedimentation basins that are to the far right in this drawing. And these are just some photos that show the bottom slab of that structure. You can also see the walls under construction, and those clear wells, above ground standpipe clear wells that I mentioned, are in that picture to the right, those 2 white towers. These are a couple of shots that show the interior of the flock sed basins. You can see here there are the divider walls between the flocculation and the sedimentation basins, and also what you see there is a number of pipes basically to try to create a uniform flow between one basin and the next, the flocculation basins, you really, when you're developing flocks, you need to take great care to make sure that you're not creating any hydraulic conditions that would shear the flocks, because that would adversely affect the settling characteristics of the particle, and you wouldn't get as clear water coming off of the lamella plate settlers as you would otherwise. This is then just the construction of the new building that's on top of the flock sed basins. There are some facilities, not many, but there are some on the Great Lakes that don't have a building over the flock sed areas. And in this case, Aqua was pretty adamant that they wanted a building, because you do have to go out and you do have to maintain these facilities. If they were outside and there wasn't a building, you would get ice formation on the top of the plates that they would have to take care of, because it adversely impacts the settleability of the water, and it would just add a lot of maintenance time and reduce the performance of the facility. Another shot of the new building, you can see it from a couple of different angles there under construction over the flock sed basins. Basically, the operating level is where you see the top of in the left drawing and the right drawing, where you see the top of the concrete. That was all cast in place concrete, because that's a water bearing structure there for the sedimentation basins. I previously mentioned the roof. This just shows a photo of the roof with the steel beams to support the roof. As I had mentioned, it was originally designed with trusses, but Amazon was taking a lot of trusses at that time for their facilities. They were on back order. So we pivoted to the beams to maintain project schedule. Just another shot that shows a section. At the top, you see a section through the rapid mix. You can see the little mixer up in the upper left. The 3 stages of flocculation, where you see kind of the flocculators, or the long, narrow paddles. And then the plate settlers are shown to the right in that top photo, which again, it looks like a truss, but those are really the support structure for the plate settlers. And then these are just some photographs that show the plate settlers being delivered on the site and then being installed in the middle of the slide, and then to the right, the finished facility there. And the long channels that you see in the photo to the right basically collect the water that comes up through the plate settlers and takes it to the filter building for further treatment. This is just a shot that shows the baffle wall that I mentioned to provide basically laminar flow coming from the flocculation basins into the sedimentation basin to provide better performance of the lamella plates. And then the photo to the right just shows a number of different mixers that are required. You can see the building on top. You can see they are all very accessible for plant staff to operate and maintain. So what are the successful outcomes from this project? You know, and this is kind of a recap, if you will, is we've talked about the inclined plate settlers, which are stainless steel. They're very durable. This is the first installation on Lake Erie, the first installation in Ohio. We've talked about the fact that they're very compact in size, which can reduce the footprint and the construction cost of the overall facility. And actually, what has been found by plant staff is that the performance actually has exceeded what they would have expected. They're very happy with the performance of the plate settlers and the low turbidity of the water that's directed to the filters. Successful outcomes on the 1908 filters and the clear well rehabilitation are, we were able to use those existing facilities with some modification to them, including how we fed the filters, putting in new backwash troughs, putting in new under drains at the bottom of the filters to take the filtered water out uniformly from the filter and replacing all the filtered media. And then, you know, overall design build, and this was progressive design build. I think we've talked about that. Really improve the delivery schedule. If this project was not progressive design build, it's not likely that we would have been able to meet, or anybody would have been able to meet the aggressive schedule. It was the collaboration between the designer and the builder that and the owner that really made this success. There were no service operations for construction, And I think really a testament to the thoroughness of the design and the construction is the new facilities were started up in less than 14 days, which was, there was more time allocated in the schedule, and that was a nice surprise. Everything started up just as we would have hoped and went very smoothly. The transition to Aqua and their staff went very smoothly as well as they took the facility over. So post-construction, Adam showed this in a plan. This is more what it looks like currently, or really showing the sequencing, I should say. If we go kind of left to right, converting the existing flocculation basin to a carbon contactor is something Aqua's planning to doing. If we then go up, the flow goes to the new flocculation plate settler facility, and it comes back around to the 1908 filters. And the Aldridge units, which were state of the art in the 50s, have since been demolished. And the existing 1908 clarifier has also been demolished. So this is what the site looks like today, or when we flew a drone over it a month or so ago, just showing the flock settler basins there to the right, and then showing the standpipe clear wells, the two white cylinder tanks, and the filters, and the other facilities on the site. As I've mentioned, treatment performance has been very good. And, this is a similar graph to the one that Adam had presented. And filter backwashes have been easily twice what they previously had been in terms of how much water they can put through the filter before they have to backwash it, which reduces the amount of waste water. In other words, water that is not sent out to the system, but is non-revenue water that ends up going to the lagoons. Settled water turbidities have been very good as well. You can see always less than 15 NTU, significantly less than 10, and then many times even under 5. Disinfection byproducts performance has been very, very well here too. And I'm going to just move through that because I know we're kind of running out of time. And I do want to touch on the lessons learned because they're important. And you've heard this theme before, but I think it's nice to summarize it. Some lessons learned are first, plan the work and then work the plan. I think we've all heard that over our careers. The planning workshops that Adam talked about left no stone unturned. We spent a lot of time together with Great Lakes and with Aqua to identify potential failure points and develop contingency plans around those points. So there were no surprises during construction, and high quality water was delivered to the customers of Aqua by their staff through construction, which was a testament really to their staff and their dedication, because there were some challenging times, as you would think, when you're constructing major improvements like this in an existing plant. Regular and meaningful communications with all stakeholders is important. That was a second lesson learned. As Adam said, we were delivering this project through COVID, and we all had to learn different means of communications and use tools such as WebEx or Microsoft Teams to conduct virtual meetings. And whenever we did go out to the site, we maintained social distancing and wearing masks, because we certainly didn't want to expose the operators, which could compromise their operation. We talked about engaging the regulatory agencies early in the process, and often, again, the project was delivered in spite of COVID. We had regular communications and information to and feedback from Ohio EPA, which resulted in an approval time of 90 days. Even with this new technology in Ohio, the inclined plates. The collaborative nature of design build allows for quick design changes. Recall that pivot that the team had to do when trusses weren't available and we had to go to beams. And then Great Lakes reached out to local vendors, and that proved very beneficial through savings and through basically partners that they had worked with before that they knew would help deliver this project on this very tight schedule. So there's a number of people, I'm not going to read the names here, that were part of this project. There's many more even that were, had a lesser part, but were still valuable contributors to this project. So I think with that, we're ready to move into questions.
Hey, thanks, Rich. Thanks, Adam. That was fantastic. Really appreciate that. Had a lot of activity in the Q&A and the chats. There's a lot there. I'll kind of bring it together, and maybe we'll have, if I can ask, maybe if we stop sharing the slides, then people will be able to see smiling faces a little bit better. We can always go back to there we thank you slide. That's good. But I think if you do the little green button at the bottom, the stop share, maybe that will help us get out of.
Stop share.
There you go. Fantastic. Great. Great. All right. Now, there's a couple that we can nibble off right away, and then I'll kind of go through, and what I'll do is I'll run through kind of the list of questions, and then we'll come back through them, but then that kind of gets your mind going. So some folks were asking, hey, is the presentation or the slides available? So the quick answer to that is yes. We post on YouTube a couple of weeks later. We always ask the presenters for PDFs of the slides. So that I'm just doing that so that folks know. There was a civil question, which we probably can knock out right away. Beams and trusses, right? So cost, seismic, trusses maybe for seismic. Was that a concern? Beams, a little bit maybe more costly. How was that covered? That's a civil one. And then we get into more, kind of environmental or project ones. And then we'll kind of knock these out. You've got some trend data that you used for your design. It looked like you looked backwards at about a 5-year window. Any reason for that? Not longer? It seemed like the trends were that it was getting warmer and more turbid, at least over that 5 years. So do you forecast that forward? So that was kind of the data that went into it. In terms of stakeholders and partners, right, you're working with Aqua Ohio, part of Essential Utilities, $2 billion, large New York Stock Exchange traded. You guys are doing design build with them. What was that like working with a for-profit utility as opposed to a public utility? If you can speak to that a little bit about it. How did that work with the engagement with Ohio EPA? Was it Aqua Ohio's engagement or HD? How did that work in terms of engagement? Your water spaces parametric modeling tool looks awesome. Does that work well when you're not doing soup to nuts, when you're not doing design build? Can you engage with somebody if you're just doing design or you're just doing build? How does that work? And your Rivet 3D BIM, awesome. Was LiDAR used to be able to put in existing models of existing facilities? And do we call these kinds of models digital twins? We've heard people talk about digital twins for process models, but do we call you were using it kind of for a process in O&M. And so, would we think of that as a digital twin or not? In terms of stakeholder engagement and public input, any complaints or comments on the use of alum? Were people worried about aluminum being in the residual afterwards in the finished water? You talked about 24/7 manned facilities, operated facilities, but low pressure membranes were also considered, which has an awful lot of automation. Was there any kind of, were the operators like, hey, don't go that direction. You don't need us because you can just turn it all on and let the membranes run themselves. A few process detailed questions, right? You're talking about surface water treatment rule, dosing, chlorine early on. Did you have to model the hydraulics of the tanks to show that they weren't short circuiting since you're using existing tankage and trying to get CT credit? Could you just do, contact time as modeled based on volume, or did you actually have to go in and measure contact and short circuiting? Incline plates, how do they work today? Why weren't they in Ohio before? A few conventional, like you've got conventional sand filters. We thought it said conventional sand filters, but can you help us understand that? Any need for polish for microfiltration? Chlorination, gas, chloramine, residual, does that set up? Did you have any concerns over brief periods of manganese treatment maybe being needed when you had Lake Erie changeover? And then, boy, we loved all this background. You made it super accessible. So we're going to get a little bit of input from you on how do emerging career professionals brush up on skills to be able to give an amazing presentation like you fine folks just delivered. So a lot there to talk through, but that kind of hits the high points of what will go back. So circling back around, beams, trusses, the civil question, right? Seismic cost. How did that factor in? You did a great job like pivoting in the middle of, but was there any cost problems there? Were there any seismic issues you wanted to consider?
Yeah, well, believe it or not, Ohio is in a seismic zone. It's not in a seismic zone like, other parts of the country. So seismic was considered by our structural engineers. The specifics of cost of one versus the other, I really, can't get into that right now just because I don't, not off the top of my head. But that pivot was able to be maintained and keep the project within the overall budget that Aqua had identified early on. So yeah,
It worked. It worked,
it
right?
it worked. It worked. It maintained schedule. The cost impacts, if there were any, could be absorbed into the contingencies, I believe. So yeah.
And we just blame Amazon and COVID and we move on.
I'm not going to blame anybody because I don't know who's on the other end of this call.
Exactly.
But it's just the way it was. Yeah.
It's the way it played out. No, that
Yeah.
makes sense. That makes sense. Okay, so now kind of drilling down a little bit, Adam, you had some data. So you did kind of a 5-year backwards window-ish. Why not longer?
Sure.
It kind of looked from the data warmer and more turbid. Was that real? Or was that just kind of maybe we were just seeing something that was kind of short term or?
Sure. No, I think, well, in terms of like why we were looked at 5 years worth of data, I mean, I wouldn't say that's something we apply, universally to every project. In this case, it was based on the quality of data, and also, they've made operational changes over the years. So, we felt pretty good about looking back 5 years based on those considerations, that's what we were dealing with in terms of looking forward at the future improvements.
Totally makes sense. Does it look like, I mean, it looked like the water was getting warmer and more turbid, but maybe that was just because it was just a short window in there.
I think if you go back longer, that's probably not, it might be getting a little warmer, but I think it looks pretty flat if you were to go back, further. Yeah.
Makes sense. Aqua Ohio as a client, right? So, I mean, they're not a small thing across multiple states because I believe Essential Utilities is the umbrella over there, and they
Right.
do Aqua state name for whatever state they're playing in. So how was it to work with a quote unquote for-profit utility as opposed to a not-for-profit, local government? What's that like?
As I mentioned, I've been doing this for a long time, and water professionals are water professionals. Whether it's an investor-owned utility, whether it's a public-owned utility, and their main drivers are always providing reliable, safe, high-quality drinking water to their customers. So there really was no difference in terms of how the project was executed. There was no focus on trying to do things on the cheap, so to speak. They wanted it done right. Yeah.
Makes sense. And then how did that work with working with Ohio EPA? Is it Aqua Ohio's relationship with Ohio EPA? Is it HDR's because that's got to make it probably a little bit interesting, right? Because if you're just doing standalone utilities, they've got their relationship, one government to one government in a sense, right? But you've got a little bit different relationship here. So how did that play out? Anything in particular for that peers would take away and say, okay, that's useful to understand that particular dynamic?
Yeah, I would say that we both have relationships with Ohio EPA. Aqua Ohio has multiple facilities in Ohio. I'm not going to state a number because I don't remember it, but it's well over a dozen. So they have an environmental compliance officer, that meets regularly with Ohio EPA, and they have a very good rapport and a good understanding because Ohio EPA, I don't want to put words in their mouth, but I believe Ohio EPA knows they want to do the right thing, and it was a collaborative effort as far as that went, Dan.
Makes sense. No,
Yeah.
makes sense.
Yeah.
A couple of details in terms of HDR's work, right? So water spaces and then your 3D BIM, right? So this was a design build, but water spaces look like a great approach that could be used for a number of things. How, can you use that tool when you're in the space of where you're splitting a design build, or do you just stay exclusively in the design build space with that? What's that like?
Yeah, no, that tool is applicable to multiple different delivery systems, from design bid build, the CMAR, to design build, that the real value of that tool that we see with it in workshops with clients is unlike a client saying, hey, can you take a look at this technology or that technology, and say, sir, we'll come back in a couple of weeks and show you what we got. Is that's a smart tool. So, if the client said, hey, I want to look at ultrafiltration membranes, and we didn't know they wanted to look at it before the meeting, before the workshop, you go in, you plug in some flow rates and some other key data, and it says, here's the size. And then even better yet, you can take it and you can move it on the site and say, should I put it here? Is it better to put it there? And it really allows kind of real-time evaluations of different technologies, supported obviously by, tech memos to follow, but
Sure.
it doesn't cause a stop in the project while an engineer has to go back and look at something. It's a
Well,
very dynamic tool. Yeah.
Okay, so a pretty fancy back of the envelope calculation. So.
Yeah, there's a lot of power, behind that tool. Yeah,
I
that
can
our
imagine.
folks have invested time in, and it's a tool we use. We can use on all projects, water projects, wastewater projects. There's no charge to the client to use that tool. We've developed it for the benefit of our clients.
Wow, wow, fantastic. And the 3D BIM LiDAR used to go and take a look at the facility and plug that in before you started playing in that space, or?
That's what we typically do, and I'll let Adam talk to the specifics, but yeah, we'll typically go in and do a LiDAR of the existing spaces. We've got some very detailed requirements in terms of, how the LiDAR should be done in order to get the best use of the data that comes into the point cloud afterwards, and how it's developed into a model. Adam, do you want to talk a little bit more about how we approach that here?
Sure. Yeah, I think, and you're 100% right, Rich. I mean, that's the preferred approach now, because we get, accurate data. In this case, I think we use the record drawings to develop our models, just in the interest of time. We were interested in moving forward very quickly. So, instead of having to mobilize, somebody to go out there and scan, and then, download the data, work with the data, that could take a few weeks. So we just wanted to move quickly.
Yeah. And in this instance too, because that filter gallery was submerged, there was no way to get access to see what was down in there and develop a model for it.
Sure.
Makes sense. Now, would we call that a digital twin? We hear lots of people talk about digital twins, right? And I hear, especially in process models, digital twins, right? Because like, hey, I can tweak it. Do you put water spaces? Do you put these 3D bit? Because you were using it in a sense like that. Like, let's talk with the operations staff and have them go in and see, okay, we're going to have this valve here. Is that going to give you enough space to be able to work around this? So would you call that digital twin, or would you not use that kind of language in this one? Or do you just avoid that language altogether because you're like, hey, I'm not a big fan of that language? I don't know.
Adam, do you want to take that, or do you want me to take a shot?
You know what? I'm not that familiar with that concept, Rich, of a digital twin, so I probably shouldn't.
Okay. Well,
Yep.
I mean, and at a high level, Dan, I mean, I think, I've heard different definitions of what a digital twin is, depending on, who you're talking to, what time of day it is, and whether the World Series is on or not. So, I mean, I wouldn't call it a digital twin, only because the way I sort of understand digital twins is it's active and it's in real time. I mean, if we were modeling the flow through the facility and looking at the turbidity and trying to predict, if the turbidity goes up, what the operators should do in order to, still provide safe drinking water, to me, that would be more of a digital twin. But again, somebody with a different viewpoint might define this as a digital twin, but not me.
Well, I was kind of in line with where you were coming from, Rich. But then when I heard you say, well, but we're using it as part of our stakeholder and to go in with the operators, I thought, well, that is kind of a process in a different way. So I was just kind of curious where you went with that kind of language. But along those lines, right? So stakeholder engagement, clearly you had multiple meetings, you had engaged with a lot of different folks. Any public input on alum as your coagulant? Any folks worried about, hey, there's we don't want aluminum in our deodorant. We don't want aluminum in our finished water. We don't want, any kind of issues there that were picked up on or people had any concerns with?
I mean, I haven't heard anything. I don't know, Adam, if you
No.
have, but I mean, they've been using alum at
Mhm.
this facility and other facilities on the, on the Great Lakes for years. So,
Right. Yeah. No complaints as part of this project. Yeah.
Okay. At least you hadn't heard anything on this
Right.
one. Okay.
Right.
So you got this 24/7, folks are always there, automation, but you're still leaving decisions in the hands of operators. So that part came through really clear. When you got into the low pressure membranes, any discussion there about, wait, maybe you're taking too much away from us because it's automating a little too much? I don't, I realize that didn't necessarily go through to the final, but when you were having those kind of discussions, were there any kind of heebie-jeebies coming from the, ooh, membranes? I don't know. It's not the same as me over here with the technology I'm familiar with in terms of kind of conventional surface water treatment.
Right. I don't recall, any concerns with the level of automation built into those, ultrafilter membrane systems. I think it can be adjusted, I'm pretty sure, depending on the level of control that's desired by the operations staff. But I recall the operations team being interested, in membranes. But again, it just came down to a cost decision in terms of why they didn't implement it at this time.
Okay.
Yep.
Makes sense. Surface water treatment rule, CT, you are looking to, hey, let's adjust so that we can get some extra time in for our CT. Was that just calculated time, or did you have to go in and actually measure time because you were going to, kind of take advantage of some existing tankage? Did you have to actually demonstrate that you got time credit for that existing tankage and that you didn't have any hydraulic short circuiting? How did that work into the process?
So I recall, Dan, that it was a paper exercise. I believe we calculated it based on the design. There's some strict criteria around what you can claim in terms of CT based on the baffling design. So again, I believe we just calculated it on paper for submittal to the EPA for approval.
Didn't require a tracer study, at least.
We didn't do any as part of this project. We didn't do any field work to verify. Yeah.
Fantastic.
Yeah, that can be done. CFD modeling can be used. This was relatively straightforward, and I don't think I mentioned it, but we did add a baffle wall in that existing clear well in order to provide better length to width to depth ratio.
And it's a square clear well, so not that complicated in terms of hydraulics. Yeah.
Pretty straightforward. How are those incline plates working today? And why were they not in Ohio before? What's in Ohio have against them? No, we'll reword it a different way. How do we get Ohio to want more of those? Maybe, I don't know. I don't know which way we want to word it, but how are they doing today? And it seems a little bit strange that it's kind of a new thing for them, right? I don't know.
Danny, okay, I'm sharing again. Just
Perfect.
going back to the slide that Rich talked about.
So you show us, yeah.
So this is really the slide that shows how well they're performing. So again, settled water turbidity was inconsistent prior to the incline plates being installed. Sure. That first year, they were still figuring out. They were installed at the end of 2021. So that first spring, they were still trying to figure out their operations. But after they got it down, you can see it's really been pretty flat ever since.
Knocked it out of the park.
So stability and high quality, and again, that's allowed them to extend their filter run times pretty substantially.
No, and that's fantastic. And so are other locations saying, hey, we want some of this, or is it starting to spread? I mean, it's not like it's a brand new thing in a sense, right? So I was kind of surprised when you were saying like, hey, it was a new thing, and I thought, well, that's it's certainly not new to the industry, right? Maybe new to locations. So are others starting to pick up on that or not really?
I can't speak to the interest statewide, but we do have a number of other utilities that we work with locally that are very interested in it. And we've got one project that one other project where we're building it into the design of their new sedimentation basins. Yep.
Fantastic. Makes sense.
Yep.
The filters, conventional sand?
So mixed media, sand and anthracite.
Sure. Yep. But you're fairly conventional, kind of going with the backward looking history. Any need for polishing, microfiltration, anything, or maybe especially not now once you've got the baffles going well. So the plates seem to be doing the trick.
The quality of their finished water is very good. Yeah, very good.
Gas chlorination, residual, is it chloramination? How's their, what's their disinfection system, if you recall offhand?
Yep. So it's bulk sodium hypochlorite that they have delivered to the site. Yeah. So it's liquid sodium hypochlorite that they inject. Yep.
Makes sense. And then during Lake Erie changeover, any needs for manganese treatment in particular during that? In terms
Sure.
of...
Yeah, they do deal with, hypoxic water. So where they get spikes of manganese. I believe they have sensors in the lake so that they can catch it, early. And they deal with it by adding, upping their oxidant, so their chlorine feed in the raw water, or maybe they inject chlorine into the raw water during those times. And so that's their operation for dealing with manganese at that plant. And we just left that all in place as part of this project. Nothing changed on the chemical feed with respect to the chemical feeds.
Makes sense. Makes sense. Yeah, no, well, and comment after comment was how awesome this presentation was. I mean, everything from let's start at the level where here's the common vocab, here's the common terms, because we've got, solid waste and wastewater and drinking water and air pollution and public health and, and chemists and biologists. I mean, the academy is very broad, right? And so we've got a whole bunch of people who are really deep in their own specialty. So you totally knocked it out of the park with that kind of like lead in. So we'll probably use that as an exemplar to say to others, spend a little bit of time at the beginning, because I'll tell you what, this is awesome. But how, and the points of learning at the end. I mean, Rich, that got a lot of people commenting on, really enjoying that. But how would you give advice to those kind of like emerging professionals to pick up on this kind of presentation style? Because we've had a whole bunch of different kinds of webinars. We all see a whole bunch of different kinds of presentations. I'm seeing a whole bunch of comments of folks saying we really liked this. So any words of wisdom to be able to help share with people?
So,
I guess Adam, besides like work with Rich and have him coach.
Right. So that's what I was going to say. So I'm going to let Rich speak to this, because I like to think he's been successful with me, Dan, in doing that. So, I don't know what his advice is, but I think he should share it.
Sure. And by the way, I guess I haven't moved in a while. The conference room I'm in, the lights just went out, but I guess the computers adjusted.
It's correcting.
Right.
We saw it dim down. So yeah.
Right. Well, I mean, like I think a lot of people, especially engineers and scientists, when I first got into this business, I was deathly afraid of presenting in front of anybody, but I think what I've learned over the years, and I've had some good mentors too, is be comfortable, know your subject, realize that your subject as well as anybody else who's listening. And the more you do it, the more comfortable you are with it, and you learn lessons. It's a little harder to do a webinar like this because you can't see the audience. I mean, when you do an in-person presentation, if you see somebody scowling or looking puzzled, you can kind of come back around and explain something a little bit differently. But here, when I say something and I hear silence, they either thought it was brilliant or they thought it was stupid, and you don't really know which. But just,
brilliant.
Right. Okay. Well, thank you for that. But no, I mean, seriously, Ed, it's just, it's great for all of us as technical people. It helps our communication skills, and the more you do it, the more comfortable you are with it.
Well, it's fantastic. I mean, certainly it's a testament to a fantastic presentation, a great team, great company. Lots of fantastic comments here in the Q&A and in the chat, folks saying like great presentation. So definitely well done. Clearly exceptional work. It's not surprising that it won an award. And we'd love to see you guys come back and look for some future ones. So this was awesome. Thank you so much for taking time out. We will turn it over to Marissa to wrap us up.
Thank you, Dan. And
Thanks, Dan.
Thank you, everyone, for all your questions. Thank you to Adam and Rich for sharing your knowledge with us today. We do have several webinars planned in the near future, so you can go to aaees.org/events and you can reserve your spot there. PDH certificates for board certified individuals for this event will be sent out sometime this week. And that's all for now. We enjoyed being with you. Have a great afternoon. Thank you.